As we have mentioned earlier, that wave is the propagation of the energy. The propagation of the energy happens because when the wave passes to the medium oscillate or have the displacement, so we can see that it gains the velocity from the propagation of the wave. Okay, so it means that we can transfer the energy through the wave, but the propagation of the energy happens continuously in time. So in practical, we are not interested in the energy itself, but in many times we are interested in the rate of the energy transfer or the power. Okay, the power which equal to the rate of the energy transfer. Rate of the energy transfer. Okay. Now, if we have an element of the medium, and we have the sound wave pass through the medium, for the simplicity, let's discuss the wave traveling in one dimension first. So we have the sound wave traveling in this direction, and due to the propagation of sound wave, we have the pressure difference between two faces of this element. You can imagine that this is an element of the medium inside a cylinder, as we have discussed before. So if the pressure on the left side is a P plus delta P, and the pressure on the right side is P, so we have that the force that acting on this element of the medium is equal to the delta P I. Okay, this is a positive x direction, and if every part of this element move due to the propagation of the wave with the velocity v, I'm sorry, we should make it clear that this is Vx. Okay, to be clear and to make it different from the V that we use as the velocity of the wave. Remember that the velocity of the medium can be different from the velocity of the wave, and the energy happen because the medium move. So what we have to look here when we talk about the power of or the rate of the energy transfer, we have to consider the velocity of the medium, not the velocity of the wave. Okay, so if the velocity of the medium is Vx like this, we can write down the power that deliver to this element of the medium, and the force exert on this element dot the velocity of this element that this element move, which is Vx. Okay, and we use this expression for the force, so we have that this is P, this is delta P time, oh sorry, it's not only the delta P, we must have delta P time the area, the surface area of this element too, right? Because pressure is the force per unit area. So if we want the force, we have to multiply the pressure with the area. So this is the PA. Okay. Time the velocity of the medium, which is the first derivative of the displacement with respect to t. And since this is a one-dimensional motion, we have that as a vector. This we have to put I here and the dot product, and we have to put I here too. But this I and I, the dot product of this unit vector, give us 1. So at the end we have the product of the delta PA times the ds by dt. Using the expression of S, that is S xt is equal to S max time cos omega cos kx minus omega t. Okay, we have that, and also using the expression for the delta p xt equal to the delta p max sine kx minus omega t. Okay, using these two expressions, we have that the power is equal to the rho v omega square a s max square sine square kx minus omega t. Okay, so this is the expression for the power delivered to this element of the medium at position x and at time t. We can see that the power is a function of the position and the time. In practice, we may answer what is the average of the power that delivered through the wave. So we have to find the time average for this expression. By definition, when we want to calculate the time average, we have that the time average of the power is parenthesis here that is used as a symbol of the average, and now this is the time average, is equal to the 1 over the period. Here, when we talk about time average, since we know that the power is a sinusoidal function, so it means that it will repeat, the value of the power will repeat itself every 1 period. So when we calculate the time average, it means that we want to know the average of the power delivered to the medium in 1 period. The average over 1 period. The average over 1 period. So, by definition, if we want to calculate the time average over 1 period, it means that the average of the power is equal to the integral from 0 to t of the power dt. This is the definition of the time average. Now, if we look back to the expression of the power, we can see that it is only this term, this psi square, which is the function of time. So, when we perform this integral, we can limit ourselves to the integral of the psi function, okay, to the integral of the psi function. And to make it simple, you can see that we can choose a position. We can choose a position to make the expression of the power as simple as possible. Okay, because the sound wave will pass through the region of the medium. So at every point, the average of the wave of the power that delivered by the wave should be equal. In this case, the wave moves in 1 dimension, and we see that all energy transfer from this part of the medium must go with the same amount to this part of the medium, and also go to the part of the medium beyond. The energy cannot disappear. That is the conservation of the energy. So, if we know the rate of the energy transfer at this point, it must be equal to the rate of the energy transfer at this point, and equal to the rate of the energy transfer at this point. So we can choose one point and choose the point that make the calculation the easier. So we choose to look at the power transfer at x equal to 0. Okay, at x equal to 0, we have that 1 over t of the integral of 0 to time t of the sine square term. But now x is 0, so we have kx here equal to 0, okay, minus over omega t minus omega t dt, okay, and this equal to the 1 over t of the 0 t sine square of the omega t dt. We use the trigonometry identity that the sine theta is equal to the sine theta equal to the minus of sine theta. Okay, we use here sine theta equal to the minus of sine minus theta, but we have the square here, so the minus sine here will disappear. Okay, so that at the end we have this sine omega t. And doing this integral, we found that this equal to this integral is equal to half of t, and we have the reciprocal of t as a factor, so at the end we have this equal to 2. Okay. This integral is equal to this term. So this integral is equal to the 1/2 or 0.5. And if we put this to the expression of the average, the time average of the power, we will have that the time average over one period is equal to 1/2 of rho v omega square a s max square. Okay, so this is the average power that transmits through the wave in the cylinder. This is a sound wave in one dimension. Next, we will define the intensity. The intensity of the wave. By definition, the intensity of the wave is the power delivered by the wave, the average power delivered by the wave over the area that the wave propagates through. Okay, so for the wave traveling in the cylinder, we have the wave traveling through a cylinder like this. Okay, and the power delivered through the area that is the cross-sectional area of the cylinder A here. Okay, so when we put this expression to the formula for the intensity, we have that the intensity for the one-dimensional sound wave the intensity is equal to half of rho v omega square s max square. Okay, However, we have the relation between the maximum change of the local pressure delta P max square with the maximum displacement of the medium S max, like this. So if we use this relation and put it to the expression of the intensity, we will have the intensity of the one-dimensional sound wave is equal to the maximum change of the local pressure square over 2 rho V. So this is the power delivered through the cylinder when the sound wave passes through the cylinder. And this valid for the sound wave in one dimension. To be careful, this formula valid only for the sound wave in one dimension only. For the sound wave that propagate in 3 dimensions, and if we have the case that the source of the sound wave, the site of the source of the sound wave is small compared to the distance that the sound wave travel, we can assume that the source is like a point source. And from symmetry of the problem, it means that the sound wave will propagate as a spherical wave. Which has the source here at the center. So we have the spherical wave propagate from the center, and the wave travel in all directions from the source. Okay. The total power delivered from the source is equal to the total power of the source that the total power of the wave that propagate out from the source is equal to the power of the source that deliver to the medium. So if the source gives the average power whatever the value of this average power, it means that the total power that propagate to the wave will equal to this average power from the source. But you can see that the area that the wave pass through, it depends on how far the wave travel from the source. Okay, we can see that if we look at this distance, this hemisphere is the half of the area that the wave pass through when it travel with this distance. But if it go further, the area increase. So we will have that the intensity of the wave, which is the power over the area that the wave pass through, must equal to the power over A. But now the area A is the surface area of the spherical surface that the wave passed through. So we have that the surface area here is equal to the 4 pi r squared. Okay, where r is the distance from the source. R is the distance from the source to the position that we want to measure the intensity. So this is R. So we have that the intensity for the three-dimensional spherical wave is equal to the average power from the source over 4 pi r squared. Okay, this is the power from the source, and r is the distance from the source. From this expression, we can see that the intensity of the sound wave will decrease with the distance from the source, which is what we have in our daily experience. If we are far away from the source, the intensity or the loudness of the wave will decrease.